So as Erin said this morning, this work have been driven by Claire, which is in the postdoc, is located in France. So due to the difference of hour, I am pleased to present this collaborative works with all these collaborators. And it is about a framework to infill missing data from freshwater data. So for this talk, in 15 minutes, I hope I will be not too long. I will just present shortly the site we have and the data we have worked on. So the first part will be to understand the link between the water quality variable and the nitrate concentration. And at the end, I will present our framework and the method we propose to infill nitrate missing data. So the site, the data come from the National Ecological Observatory network, and the three sites, you can see the three sites is, one is there, just in the middle, one is there and one is there. So Macquarie is in, so this one is in northeastern Colorado, and is so these three sites are different climates. So in northeastern Colorado is hot summer and cold winter. We have the Lewis Run, which is here, which is approximately to 60 miles west of Washington DC. So the climate is temperature temperate and humid. And the last site we consider is Caribou, which is in Alaska, and the average temperature is around -3 degrees. So on this site, we have collect the nitrate sensor data and the water quality sensor. And for the nitrate sensor, we have one data point for every 15 minutes. And we have all these variable as water quality variable. So we have three sites. So just some explanatory analysis and present some variables and the nitrate concentration. So you can see on this nice box plot on the three different sites, we have a quite very heterogeneous data between sites. So you can see that the difference is the nitrate for the three sites, and also for the different variable. For example, you can see that Macquarie with the elevation is far away from the other two creeks, and Caribou and Lewis Run. So we have some different heterogeneous data between sites. We have to take into account in our analysis when we explore the link between the variable and the quality variable and the nitrate concentration. So our model, we propose to explore this relation and to get some nonlinear relation, possible nonlinear relation between these variables and the nitrate concentration is a GAM, so generalized additive mixed model. Additive mixed model, yes. So in this equation, you have this sum is just the sum is for each variable, and the S is just to represent the nonlinear effect, which is will be using some spline to have some smoothness and some nonlinear investigation for each covariates. And we have this model, one model for each site, because we have heterogeneous data. And this small guy is the error, and the error is modeled by NARMA error, an autoregressive moving average, to take into account that we have some time series data. So we have one data point every 15 minutes. So this basically is the model we want to deal with. But we have some computational issues. The first time Claire tried to work with this model is, as we have a lot of data, is too hard for in computational time aspect to run this model. So to overcome this computational issue, we move to a two-step approaches. So the first step, we use a generalized additive model, and using some to model the non-linearity of each covariate, and we have a stepwise variable selection procedure to choose the best model, and also to not have an overfitting with the GAM model with a non-linear effect. We fix the smoothness with a maximum value of the degree of freedom. So this is a normal GAM. And after we get the residuals, and on the residuals, the second step is to model the dependency between the data points, because we have each data points at every 15 minutes. And we will model this by an ARMA model. And so the best ARMA regression model is been using the Akaike information criterion to take the best ARMA model. So this is in the two step to be able to get this model performed for each site. So I will present a little bit some results here to understand the link between the variables and the nitrite concentration. So you can see the different percentage of deviance explained for the different sites, so Macquarie, Caribou, and Lewis. So 70%, 90%, and 80% of deviance explained by the variable. But we have quite some heterogeneity between sites. If you can see, for example, on the specific conductance. So it's the first row here. I will zoom a little bit. So this is for the specific conductance. You can see that the relationship is completely different between the three sites. We have quite a short confidence interval for this effect, but some are very wide. So for example, on the log of the turbidity, you can see that these confidence interval are quite wide, so it's quite difficult to do some inference on the relation with this wide confidence interval. So to have more insight between in our model, we looking at the importance of the variable in the generalized additive mix model. And so you can see that to move with a simple GAM on the right, on this table, on the model performance, you can see just to have to explore if we want to choose the model regarding the AIC criterion. It's clear that taking into account of the dependency between the points improve a lot the model. You can see that the AIC, for example, dropped to something which around 6,000, something that negative 44,000, and we know that the best model is to get the AIC the smallest as possible. And for these all sites, these three models, we have 97% of the deviance have been explained. So the model is quite a good fit. And now if we're looking at the importance for each site for different variable, you can see, for example, for Macquarie that so Macquarie is the square here. So Macquarie, you can see that the percentage of variable importance of each variable is quite small. So in fact, is for this model is the ARMA part. the autoregressive part of the model is quite very important. But for example, for Lewis run, which is a triangle, there, you can see the time effect, all of this has quite a large influence. And in fact, is the covariates explain a high percentage of the deviance explained by the model. And the armor part is not important. And for example, and in the middle, Caribou, you can see that can detect some importance variable, which is elevation. Oh, in fact, I lost my pencil, sorry. So is my finger, it's not so good, my finger. And you can see the time effect take a lot of importance, and the elevation is very important for Caribou, while for the armor part is not also as important as in Arikari. So this was the first conclusion of this part, to understand the link between the water quality variable and the nitrite concentration. So I think we succeeded to show that our model provide a useful method to understand some non-linear relationship between the nitrite and the other quality variable, with a high percentage of deviance explained by our model. And the result we have seen that there are quite different relation between the different sites. So as the perspective of this work, it can be to explore similar pattern in other sites, using some other site from the NEON database. And now we can use this model in our former work, from the goal on this work, which is to infill the missing data. So we will use this model. So I'm moving now in the last part of this talk, which is infilling nitrite missing data. So first of all, I will present some result on a simulation study, and after on the real data. So on the simulation study, we used in fact the real data, but we removed some observed data to create some missing data. So we have done two kinds of simulation study, and the first is for the missing point data. So is the meaning that we randomly remove 20%, 30%, or 40% of the observation across all the time. And the second part is about missing sequence of data. So now we randomly remove 10 data points in consecutively days or in week of observation. So we remove sequence of data. And the second goal is to infill, for example, the time series from Arikari. And you can see that this is observed time series, and the data are from October 2018 to October 2020. And you can see that there are some some trouble. We have 3 months, or we have some technical issue with the nitrite sensor. So we don't have this data, completely missing. And after we have also some missing data. And on this, we have around 20% of the data which are missing here. Okay. So what our method are doing? So first of all, for each missing data, we're looking at if for this specific time, if there are some missing data on the covariates variables. So so the first question is if the data are for all the covariates are available. If they are available, we can use the generalized additive model. So we go in this path, because we have the the missing data for the nitrite. We have the data for the other covariates. I hope I'm clear. So we can use the generalized model to do a prediction for this specific data point. And you use this to do the model prediction. And then you can have the prediction and also to get the prediction interval. If we have some missing value in the covariates, also at this specific time point, we will use an autoregressive integrative moving average model. So just based on the data from the nitrite concentration. And we go on this path and we got the prediction. So we have two ways to fill the data. Okay, so I will present some results. So to evaluate if it's going well, our framework, we evaluate the root mean square error, and we looking at also the proportion of reconstructed data within the precision interval. What is the precision interval? Is the detection limit of the sensor. So if we're looking at very quickly on the RMSA, is depending the percentage of remove the data, 20%, 30%, and 40%. So they don't have different, it's the same kind of result. And it doesn't take finally even more missing value, it will not affect the performance. And similarly for the proportion of reconstructed data within the precision interval. But now, if we're looking at these are more interesting, this two box plot, this figure is when you remove some data from sequence of data in 1 day or 1 week. Of course, we expect this result that if you remove a longer sequence of data, we will have more trouble to reconstruct the data. It's still working, but is, of course, if you just have 1 day of missing value, is easier for our model to reconstruct the data. So this result makes sense. So to be more clear, some pictures, it's always nice to have some pictures. So the green point are the predicted data, where we the black are the original data. So you can see that this is on the Macquarie site. So, and the gray shade is in fact the sensor detection limit. And you don't see the prediction interval around our prediction because it's very, very narrow. So it's a meaning that is very, very accurate. And for the second, this picture, you can see that on the original data, these have been completely missing. So we don't have this data. It was completely missing. And you can see that even our prediction is still in the sensor detection limit. And this is on the C part, it was just to see a pattern when we have an increase of the nitrate, and you still predict pretty well with our model. So what is the difference between using the GAM prediction or the ARIMA prediction? So using the GAM prediction is the meaning that you have all the information at the missing data point at the time t. So it's still it's quite that when we just only use the ARIMA part, we don't use the covariates. It looks like that the prediction interval is increasing. So this part is just only with the GAM prediction, with the ARIMA prediction, And this is example is when, in fact, we use both, because sometimes you have the variable available, and sometimes you don't have the variable available. And you can see, for example, if a zoom is at this stage, is that this mean that it will be using just only the ARIMA model. I'm not sure if I was clear on this part. Okay. I still some time, I hope. Yep. I think I have 2 slides. Okay. So now, second goal, our last goal, it was to, it's not simulation, it's about the real data. And now we try to infill the Arikari time series. So in the first, on the top left, you can see that we have a good prediction, we think. It looks like a good prediction. And which was more challenging is on this part of the data. So you can see that the dark point are real data. So you can see that there are a clear peak of the nitrite at this stage. And the green are our prediction. And it looks like good because it looks like it's following the pattern of the nitrite concentration.
Benoit?
Yes.
About 2 minutes.
It's perfect. My timing is perfect. Thanks, Kerry. So in this case, you can see that we have a long 1 day of missing data. And even in 1 day, we, of course, at the beginning, you can have the intuition, but at the beginning, the prediction interval is quite okay. And after is increasing because you don't have the information, but the backward information, the previous information, but it's still in the detection limit. And now, okay, everything that cannot be good. So you can see this, we have some very high prediction. So this looks like a very not a good prediction, but is in fact come from some abnormal values on the covariates. So is meaning that this time it looks like we have some anomaly on the covariates, which affect, of course, our prediction for the nitrite. So maybe this you think is quite bad, but we can see that maybe in the future we can use this to detect some anomaly. Conclusion, because I have still 1 minute. So for the conclusion is the main conclusion that is our approach performed well at predicted the value of the nitrite concentration, where we have some missing data sporadically across the time. Is performed less well when we have a long period of continuously missing observation. Some perspective, we have used the GAM generalized additive mix model for when we have all the covariates observed, but sometimes when we have one covariate which is not observed, we don't use it. So we need maybe to improve our framework to use it even if just only one covariate is missing. We have some idea. And of course, we can generalize this with oversight from different freshwater. Thanks a lot. I'm on time, so I'm done.
Thanks, Benoit.